for the PCA across the principal component, that answer is x1 tilde, x2 tilde, x3 tilde is not matching. If you can kindly help us on that.
And so could you please discuss also from the same paper projection direction how we find
projection
of
direction?
PCA? Yes, sir.
Okay. Yeah, that is the in projection direction is the eigenvector direction which have the principal direction. No, sorry. So principal direction is that direction which have the maximum eigenvalue. That's how we used to do. No? If it is one dimensional or two dimensional, so wherever we want to project it in that dimension, the maximum eigenvalue, the eigenvector of maximum eigenvalue is going to be the direction of projection. That is the PCA does actually.
And the projected variance is basically the largest lambda, isn't it?
Yes. Project. So largest lambda value, eigenvalue.
Projected variance.
So when we have a first, we have to find first principle, no? Then it's lambda 1 projected variance.
Sorry. Could you? What you are saying?
Sir, when we are finding PCA with respect to first principle, then the projected variance is lambda 1.
Yeah,
And
lambda value.
And if we are finding with respect to second principle, then it's lambda 2.
So we arrange in the decreasing order, right? The eigenvalues. So first component is going to be the greatest eigenvalue, the maximum variance is going to be that.
So can you take this August 2024 paper? Then it will help.
Just a second. Just a second. First wide. I hope my screen is visible, right? To all of you.
Yes, sir.
Okay.
So if you go to question number 15, so there you will get.
I don't have old question paper right now. I have.
No, it is August 24. I'm saying August 24. It's very recent, hardly to.
Yeah, but this time I don't have. So can you tell me the whole question paper, or you can share in the chat a screenshot of that? That would be good also.
I'm sharing it on the chat.
Yes. Somebody is sent the link of question paper, I think. Okay. This website. Okay.
These are the same question actually. Sir,
is this session being recorded?
These are the same question. If you find out the PCA, the answer, the covariance matrix is okay, but the PCA answer is not matching.
Sir, is this session being recorded?
Yes, it is live now on YouTube. So consider the following data. Suppose we want to project the data on the one dimensional space using PCA. So the sub questions are there on the basis. Covariance is this, which is the principal direction that is chosen for the PCA. So that is the eigenvector we'll find of A transpose A, right? Of the eigenvector of the covariance matrix, and eigenvector of the covariance matrix, which have the maximum eigenvalue. That is going to be the principal direction. Okay, once we project it, so what is going to be this one?
This part answer is not matching. We can slightly. You can work from the covariance matrix, and the eigenvector is already there in the earlier two answers. You can take that, and then you can simply work on this one. So answer is not coming.
Okay.
You can take from the answer the covariance matrix or the eigenvector, and then try to
So
get this.
which one is the covariance
Yeah,
matrix
second
here?
one, second one. Yeah, this one is the correct.
What is this? Okay.
Yeah, I think this is the second one.
So is this correct? This is the second one. The covariance matrix is this one, right? I think all of you have tried it.
Yes, sir. Second one was correct.
Okay.
And also the eigenvector is also in the next question. Eigenvector against the lambda maximum lambda, that is also there in the next question. Then from there to x1 tilde the answers are not coming. Yeah.
So this is the okay. This is the covariance matrix. So eigenvalues of it is going to be 2 minus 2. Just a second. Let's quickly do it. If it is 3 cos theta. Okay, otherwise let's do by hand. So what are the eigenvalues we have? All of you have tried it, no? What are the eigenvalues we have for this matrix?
I think we got one eigenvalue as 1 by root
Sir,
3.
could you please calculate?
Okay, so here it is.
The lambda will be 0 and 2.
0 and 2. So a
0,
minus
0 and 0, 0 and 2.
lambda I it is going to be. So here it is going to be minus lambda, minus lambda, minus lambda. This is going to be a minus lambda I. Now determinant of this is going to be 1 by 3. So this is going to be 1 by 3, or what is going to be the determinant here? This is 1 by 3, or what we will do here? Here it is a multiply.
It is 1 by 3, 1 by 3.
No.
1 by
What is
27.
going? 1 by 27. This is going to be 1 by.
The covariance matrix will have 1 by 3. Yeah.
This is
1 by
going to
3,
be this
1 by
one,
here.
and the rest is 2 minus lambda, and this is going to be 2 minus lambda square minus 4, and this is going to be plus, and here this will, if we cross this 2, then this is going to be lambda minus 2, sorry, 2 2 lambda minus 4, and this is going to be plus 2 plus 4, and then after my plus 2. So this is going to be 4 minus 2 minus lambda. This is going to be 4 lambda minus 4. So this we cancel out. This we cancel out.
Sir,
And
why
here it is.
Sir,
1 by 3
minus
cube?
2 lambda.
So where
4
is it? Sorry?
minus 2 lambda. So in
Yeah, this is here, no? Yeah.
Sir, why is it 3 cube?
3 cube. Sorry. Yeah, this one.
Yes, sir, why?
This is this. If you do it, it will be, this is a matrix property that if you have a scalar multiplication within some matrix, See why it is, this is 1 by 3, then it will be multiplied with, each
Yeah, 3 columns.
3 columns,
All,
not only
all
3
the,
columns,
all the rows
all
are.
entries.
Yes, okay.
Yeah, so if you take it out, finally this will be 3 cube. Here is order is 3 cross
Okay.
3. So this is going to be 3 to the power 3, and finally we have 2 minus lambda cube. Okay, let me open it. 2 minus lambda, and this is 4 plus lambda square minus 4 lambda minus 4, and this is going to be plus 4 lambda, and this is minus 4 lambda. Okay. Oh, I should to even know they easily can find it. So this is going to be, finally this will be cancel out. So 1 upon 27, and this is 2 minus lambda, or 2 lambda square minus 8 lambda, and this is minus lambda cube. Okay, sorry, why I'm opening it? To open 1 by 3 cube, and this is
no need to open.
this one, and this is lambda square, or we can take out lambda, and lambda minus 4.
Yeah, yeah.
So now we will equate it to 0, and this is lambda is equal to 0 and 2 and 4. So these are the eigenvalues we'll get: 0, 2 and 4.
Yeah, 4 to 0.
Now this is 4 is going to be the maximum one. So this is lambda 1, lambda 2, lambda 3. So this is going to be the order: lambda cube, then lambda 2, and then lambda 1. So just a second. So eigenvector now we should to find. We need to find here for getting the eigenvalues. Sorry, eigenvector. So for 4 we'll get it. So that is going to be the principal. Principal eigen. What is that? Principal component.
Principal direction.
Yeah, principal component, principal direction. The eigenvector corresponding to this eigenvalue.
Highest.
Highest eigenvalue. So here it is going to be. So finally we'll get here, if we do a minus lambda 1 I, so we will get here, and then x is out equal to 0. That's how we'll find the eigenvalue. So this is going to be 1 by 3, and I made a wrongness.
So I think it was lambda 3, no?
See, I one thing I made a mistake here. This is 1 by 3 a. This is our a, no? So a is 1 by 3 this matrix, then lambda I. If we do it, if we subtract it, this should be multiplied here. So I made a mistake here.
Pardon?
This if we subtract, what we'll get? If we can easily subtract it. Okay, this is going to be each time 2 by 3 minus lambda, right? Or maybe this is going to be 3 lambda here, and then 1 by 3, and then finally make it out 1 by 3, and then we have to find the determinant. I made a mistake this one here. So this is going to be 3 lambda everywhere. This is 3 lambda.
So the
Here is-
eigenvalues would change.
No, calculation we have to do again, no problem.
Sir, actually, I'm getting lambda as 0, 0, and 2. 4 is not coming. Can you just?
4 is not coming, no? I made a mistake.
2 actually.
Just a second.
It is safer to take, I think, the complete matrix elements without taking the common outside. In such calculations, it is required.
So let's do by calculator in a fast
Okay.
mode because we have only
Okay.
the fixed times. So here it is. Can you tell me the entry? This is 2 by 3 and 2 by minus 2 by 3. Then 2 by 3. And then
minus 2 by 3,
minus 2 by 3,
Only diagonal elements
2
are
by 3,
2 by 3.
minus 2 by 3.
Okay, only the diagonals are positive.
Yes, sir. Sir, 2 by 3.
This is just 2 by 3.
Yes, sir.
Okay.
Minus 2 by 3, 2 by 3.
So here, eigenvalues will get here 0, 0, 2. So we'll get only the eigenvalues 0,
Yeah, I'm
0,
getting
2.
also the same 0, 0, and 2.
And the eigenvectors are going to be for the 0 eigenvalue here. Okay, this is the first eigenvalue. So we want for 2 only. So for 2, it is going to be here for eigenvalue 2. The eigenvector is going to be this
Yeah, 1 minus 1, 1.
1 minus 1
And
and
then
1.
normal, and then unit vectorize it, normalize it, 1 by root 3.
So this is going to be the principal direction. So principal
D option.
Yeah, the first,
So the
third
magic.
option, last option.
This is
Yeah.
because we have to normalize it.
Correct.
So this is going to be the fourth option. This one.
That is for the
And now-
main vector. And what about the other vectors, sir? The other eigenvector corresponding
Other
to 0?
eigenvector are going to be that is not our principal direction. That is, see here if you see in the PCA is just a projection. In PCA, what we used to do, we used to do the projection, but projection is a different manner. If you see, sir is also saying, I think here here sir is not saying, but in MLT, if you see again, you will do the PCA. So in PCA, what we are doing, we are doing only the projection, but projection is a different manner. We are doing projection. The formula is different. What is exact formula is something they can know. We have to first we have to write like this, and the direction we have already fixed. The direction is going to be now the 1 minus 1 and 1. So this is the direction here, and this is 1 by 3. So this is going to be the principal direction, and other eigenvector here. These eigenvectors are going to be we'll use in the projection. Okay, if you see then the projection formula of the PCA, it is vector A and B. If you want to project A on B, so the projection formula is going to be A transpose B. Okay, and A transpose B,
D.
and then B, and then
B.
here A norm square. This is the projection formula. But if you see here the projection formula in PCA, that is a different. We'll project each time on this principal direction. So we'll take what? We will take whatever the vector we have. We want to.
How did you get this direction? 1 minus 1 and 1?
That is what the greatest eigenvalue have the eigenvalue.
Greatest eigenvalue, if you take the eigenvector, you will get this. Well, it will be 1 by root 3, sir, not 1/3.
1 by root 3, no?
1 by root 3, 1 minus 1 and 1.
Yeah.
So this is 1 by 3 or sorry.
Yeah,
I
1
just
by
wrote
Yeah.
one.
So my
1
question
root
here
3.
is, sir, I got your point. My question here is, if you get x1 tilde, if you calculate x1 tilde, it will be 1 by root 3, basically the xi original xi figures, they will be basically what? Original xi figures will be 1, 1, and 1. So 1, 1, and 1 transpose times, you have to do a dot product with this principal vector. Into that is into and the same vector. So 1 by root 3, 1 minus 1, 1, 1, you will get the x1 tilde. You have to add also the x bar part.
Yes. That
X
is
x
what
bar is 1, 1, and 1. That you have to do it dot product with the another vector. So where is that another vector?
Another vectors are these. Okay, just a second. So
Yeah, so that vector
another
is that vector you have to mention here.
Yeah, those vectors are one second.
That will be required for the X bar part.
1 second. So let's go to our exact formula then.
It will be X bar transpose times the other vector U2.
Yeah. X
Into
bar
it-
transpose U2 into U2.
into U2. So plus the X.
And this U2 is of the second eigenvalue.
Yes.
Second highest.
Corresponding to the
this-
eigenvalue,
yeah.
eigenvalue 0.
So this is required to be considered in the one dimension also.
Correct.
Am I right, no?
Yes, perfectly right.
Yeah.
Srikanth.
But it is not considering.
No, it should consider. No, it is considering. It is considering, but the answer is not matching.
Yeah, that's in the answer is it is not considered.
Yeah,
right?
it's not coming. So because I have also tried with this with the other vector and done this, but the answers are not matching. I don't know if anybody has tried. If anybody has tried, they can also share the answer. I can tell my answer, but it is not there in any of the options. So that's the reason I'm asking this question.
So here it is the formula finally we have. So see, this xi is our
Original
vector,
data set.
original vector.
Yes.
And uj, see this delta is running from 1 to m. So uj are actually here the eigenvectors, I think, just a second. And the second one is
principal first highest eigenvector.
Highest eigen. So these are the eigenvectors we have.
Yes, right.
And next is we are multiplying with the mean,
Yes.
mean vector.
Mean vector with another vector, yeah.
And this is again the rest all, no?
Rest of all other vectors other than the highest
eigenvalue. So what is the final formula is that? So this is here. So this is the greatest eigenvector. Okay.
Correct.
Sorry, eigenvector for the eigenvector which have the greatest eigenvalue.
Right.
And these eigenvectors are will be multiplied by the mean of the mean of the whatever the vectors we have given. So the PCA formula is if I will write, suppose I want to write the formula for this one. So formula is going to be, so let me write the eigenvector properly first. So
sir, you can write down the two eigenvectors first, then it will be easier. What is U1 and what is U2? You can write down.
Write down the formula, sir. Write down the formula
Yes.
first.
Write down the formula and then write down V1, V2.
Formula is also confusing us. So formula.
Yes. So this is these are the eigenvectors. Okay, these are the eigenvectors we have. This one.
Yeah, that is okay.
That is okay. Then you can write down the formula and then let us see.
Now the formula is I want to the only one direction. It is in a principal direction. So this is going to be the greatest. Eigenvalue which have the greatest eigenvector. So eigenvector which have the greatest eigenvalue. So the x tilde, let's say x1 tilde is going to be the
x1 transpose x1.
Yeah, this is going to be. I'm saying original vectors
original value is x1.
Write down the formula, sir. Write down the formula first.
X1 transpose. And then V1. Okay, so let me again the formula. Let's say U1.
With sigma, write the formula with sigma.
Yeah. So no. So here we have only 3. No, that is for the more for the.
No. My question is
for only this case only I'm writing.
No, it will be x1. It will be x1 transpose times U1 into U1 into U1 into U1 into U1 plus. X bar transpose x bar.
Now the mean. Now the mean will come.
Mean transpose.
Now the mean transpose and then U2 will be there. Okay, then outside U2 plus
x
bar and U3 and U3.
Then
for this case, this is the formula.
Sir, one doubt. Shouldn't we have x bar transpose in U3? The last term.
Yeah, here is also. Yeah, here is means it will go the same.
Yeah, that's what I have. Yeah.
All the vectors other than the principal vector will be in the subsequent part.
Yeah. So here the main thing is that this have the maximum eigenvector which have the maximum eigenvalue, and rest all the eigenvectors see the multiplied by the mean. So means inner product with the mean. So this is the difference between the original projection formula and here in the PCA formula. See, in the projection formula, this is, if you see, this is not the case here. Okay, but only one way, only this is what we are doing in the, you see, this is only part here written, but we are in the PCA, we are doing this mean with the mean also, the projection formula written with the mean also. So this is the difference between the PCA formula, which is also a kind of projection, but different. The difference between the normal projection and the PCA projection.
Here, how it is correlated with the normal projection? In the normal projection of B onto A, na? Here, in the formula, projection of B onto A. This is the formula for that.
So this is what, this is the main one. Here, projecting on, no, on U1, the eigenvector, maximum eigen.
On U1.
On U1, which have the maximum value.
The projection of X1 on U1.
X1 on U1. This
And
is the, we are projecting X1
here in
U1.
the formula. Here in the formula, projection of B onto A.
A on B.
Projection of A on B.
A on B.
on A. This is formula for projection of B on A, na?
No, A on B. I mean, that is what we are using the direction.
Yeah, correct. A on B.
So suppose suppose there is another vector. We want to project A on B1 and B2. Okay, suppose we want to project A on B1 and B2. So what is going to be formula here? So formula is going to be B1 here and B1, and again it will be added A transpose. Here is again B1. So B2 outside B2, and then norm of B2 square. So if more vectors are coming, then projection formula is like this. Means if it is again, if you want to add like third vector is there, then I will add. Means one by one we'll do the projection here.
If it's A on B, sir, if it's A on B, then it should be B transpose A.
Yeah, that's what I'm calling. It should be B transpose A.
B transpose A.
Projection of
anyhow,
A.
what I mean to, if you are doing A transpose B or B transpose A, it doesn't matter. The reason is we are playing on real number and we want to find just the inner product. Okay, so it doesn't matter. Here it will not matter. If it is in complex,
it is a scalar.
Okay, it is a scalar.
Because this is going to be scalar, no? Each time it is. So it doesn't matter. We just need to want to multiply. Means I want to just find the.
We remember the formula like that. B transpose A into B. Right?
So can you now write down the other two vectors, U2 and V2 and V3, U2 and U3. U1 is known. How you are getting the U2 and U3 corresponding to the lambda 0. So what is
lambda
that?
0.
Yeah, lambda is 2 and 0 0, na? 3
0 2 0 0 2 0 0, sorry, 2 and 0 0.
Corresponding to 0, what is U2 you are getting? Yeah, so against 0, what is the
for this one we are getting
1 by root
1
3,
upon root 3, 1 minus 1 and 1.
Minus 1.
This
Against
is what
U2, how U2 what you are getting? U2.
Okay, so here the U2 is sorry. Okay, here it is. And for for 0 eigenvalue, we'll get 2 eigenvectors. So this is here. So for 0 eigenvalue, you can see this is the here 0 eigenvalue, and eigenvector we are getting 1 1 0 and minus 1 0 1 1 1 0. So this is going to be.
So that will be 1 by root 2 1 1 0.
1 upon root 2 this one, and here it is going to be minus 1 0.
For the same 0, we will get another value. How? Orthogonal.
See, no, this is repetitive, no? So,
Hello?
see, here the eigenvalues are repetitive. So, we are getting 2 eigenvectors.
So, when we will calculate, sometimes it happens, when we calculate with the 0 eigenvalues, then the same value comes.
So it may not. So okay. So the problem here again. So you asked a good.
Actually,
suppose. So what we will do in that case?
What Srikanth is telling.
The problem.
I'll tell you. What Srikanth is telling, it's a very regular problem everybody faces. For example, in this case, we look at 2 lambda. Lambda value 0 is occurring twice. Okay. So what he's asking is, so if you take lambda as 0, you'll get 1 unit vector. The third one should be orthogonal to both. So
yes,
that is what.
Yes. So that is what I was. So you know, right? So you are taking. So the third one, if suppose you are getting only this eigenvector.
Yes.
So automatically, but only one.
Yes,
So the
automatically.
third one you will take the orthogonal to U1 and U2 both.
Right. That is what he is asking. So
Okay.
we'll go in that.
My question here is that suppose most of the question is throughout the course, only we get sometimes random by visual, we just write the third one. Suppose the vectors are two other vectors are root 3 by 2, root 5 plus 2 by 3, like that. Then how we will decide that the third one will be the orthogonal to both of these? Just a standard method formula to find orthogonal vector out of these two vectors. A standard
Gram-Schmidt process. You will find using the Gram-Schmidt process. You will have to do the
very long process.
So this is an algorithm, no? So this is an algorithm. This is not a theorem. This is one algorithm, and this is done by only the computer. You just need to know. We have to find the third one which is orthogonal to rest 2. Okay. You have to know this theory at least. This is what the theory.
Either it is easier than we can do. Otherwise, go to the Gram-Schmidt only. There is no way otherwise.
If it is asked in question in exam, so surely it should not happen. First thing, if it is happening, then it in exam very less chance to come such kind of problem. You have to do the Gram-Schmidt. If it is asking also, it will be very easier. It could be a kind of this one. Then your vector could be of 1 0 0 and 0 1 0, and suppose eigenvectors you are getting this kind of, then it is a guessing. No? Third one is going to be just 0 0 1 because these three are orthogonal to each other.
In such cases, it is easier because we are friendly with this.
So problem is created like that, but you have to know the theory at least.
Theory is the Gram-Schmidt only.
Yeah. Anyhow, the Gram-Schmidt process you have to follow to find the orthogonal vectors.
Okay. A second question related to this. Sometimes confusion occurs. Suppose we are calculating the eigenvectors, then comes x1 is equal to x2. Okay. And second time comes the x1 is equal to minus x2. In the same case. Okay. Then in the second case, if minus 2, which one we should take? Whether we should take the free variable which are coming, or
sorry. Once again. This x1 and x2.
X1 is equal to x2 one time, and second time it is coming x1 is equal to minus x2.
No. This original vectors you are
two vectors. Suppose we are calculating for one eigenvalue, it is coming x1 is equal to x2. In the second time, it is coming x1 is equal to minus x2.
No. What you are finding x1 and x2? What is the x1 and x2?
Eigenvector.
So if we are calculating eigenvectors, like we are putting value lambda suppose is equal to 1, we are getting value as x1 is equal to x2.
Okay, and x1. Okay.
Yeah. In that case, suppose our matrix is we have to calculate the eigenvectors at that time. First time we have taken the free in both the cases, free variable is x2. Free variable is x2. Okay. And then we are taking first time the 1 0 will come. The second time 1 1 will come. In the second time, whether we should take minus 1 1 or 1 is minus 1. Because when we take the other one, the value changes, and the other value is also affected. Do not match with the answer. So what is the standard method to take?
So just
you got my question.
Basically, sir,
I got your question. Can you tell me? I got your question. Just a second. I got your question. Can you tell me the equation? What is the equation you are saying? X1 is equal to x2.
Suppose 1 1 1 1 is there. All the 4 are 1 1.
All the 1 1. This one.
Solve it. No. That is 2 by 2. 1 1 1. Just take a small value. 2 2.
Okay.
1 1 1 1.
Okay. And then I just need to find the eigenvectors.
Yeah, another one, 1 1 and minus 1 minus 1.
1 1 minus 1 and minus 1. So you just need you are saying so You want to calculate, like I need to calculate eigenvectors here.
Eigenvectors here.
Okay.
Both the case eigenvector will be same, no? It will be x1 plus x2. X1 plus x2 is 0. So if I take x1 as 1, x2 will be minus 1, and then normalize it by 1 by root 2. And second case also will be same.
No, in the second case, x1 minus x2 will be 0.
No. So x1 plus x2 will be 0. Na? Second case 1, 1. Na? 1, 1 is 0. Na? So minus 1 is 0. So minus x1 minus x2 is 0 is as good as x1 plus x2 is 0. So the vector is 1 by root 2 times 1 minus 1. So both the case, the eigenvectors are same.
Sorry. Sorry. Please change the actually minus 1, 1, 1, minus 1. Minus 1, 1. Minus 1, 1. 1 minus 1.
1 minus 1.
Okay. And another one is 1, 1, 1, 1.
Okay, got it. So
what I find out, the simple question is that which one we should choose?
Which one?
Suppose x1 is equal to minus x2, it is coming, then we have to choose one. Either x1 is equal to 1 or x2 is equal to 1.
Yes.
The answer will change, na?
Sorry.
But Srikanth, the answer will change, the vector will change, but ultimately your final answer will not change. If you take x1 as
sometimes it is, yeah, got your point, but sometimes it clashes with the answer in the
question. Sometimes you are right.
My question is this, what we should do, the only one decision should be there, na? In mathematics only one decision, na? Which one is correct?
So you are saying this is your x1 and this is your x2.
Just a minute. You change here, na? This is 1, 1, 1, 1. Another one is minus 1, 1, 1 minus 1.
In which direction you are saying? See, this is 1 minus. So what you are choosing here? I don't know what you are choosing here.
When we calculate the eigenvalues, na, for a eigenvector for a eigenvalue. Okay. After getting ultimately we get this equation. We get this equation to solve x1, x2, so that we can get the eigenvalues.
Okay. For this matrix you are saying. Okay, fine.
Yeah.
Okay. Then
we go there and we will x1 is equal to 1, x2 is equal to 1. No problem at all. Okay.
Yeah. Okay. Here, what if you are getting this equation? Okay. So here it is going to be, we'll choose x2 is equal to any one of the x2 is equal to 1, then we'll get here eigenvector as 1 and 1.
1, 1, 1, 1. Okay. No, but then, for this it will be x1 is equal to minus x2, no?
No, complete it. Let complete it. So you will get 1, 1. Then let's complete it.
In the second equation, we will get x1 is equal to minus x2.
x1 is equal to minus x2. Okay. Then
for the second value of the second eigenvalue, then here we can choose either x1 is equal to 1 or x2 is equal to 1. If you will choose x2 is equal to 1, then x1 will always be minus 1. If you choose x1,
minus 1 and 1. Correct.
Okay.
So you are saying you are saying if in case we are choosing x2 is equal to minus 1, then it will be 1 and minus 1.
Yeah.
Correct.
Yeah.
So which one I will choose?
Yeah, which one I will choose? This is my question.
So see, these two directions are, first of all, these two are same. Okay. These two same.
Yeah, I know. But
these two are same. So whatever you will choose, you will end up with the correct answer. The answer is going to be same.
But when this eigenvector is being used somewhere else, no, then answer changes, no.
So here, okay. So then you have to go with the matching option. You have to go with the match option. You have to go with the whatever the correct matching.
Okay. We have to check it, right?
Yeah, you have to check it. So
in this particular case, you have written U1 and U2. Can you find out U3 from U1 and U2 both are orthogonal? I'm not able to find it. Can you just check?
No, why you are finding now
not this one. You go above, slightly go above. This U1 is basically 1 minus 1 1. U2 is 1 1 0. From that, you are getting U3 as I think you have mentioned 1 minus 1 0 1, isn't it?
No, in this case we are getting, but suppose not getting, then you have to follow. Here
No,
we are
just
getting.
in this case, you just do this example, na? 1 minus 1 1 and 1 1 0. How will you get U3? Just calculate how you are getting U3.
So U3 is here. I have just.
I'm just calculating. Yeah, I was just I'm not getting it.
So we are getting 2. So okay. So let me go with the equation here. So where is that? Just a second. That. This is the. Here this one.
So can we start the revision session? This
Yeah.
Discuss later.
Alok, for sir, I did this. Sir, if you want to find V3, just set y is equal to 0. If you set y is equal to 0 and then you solve the equation, you will get it as minus 1 0 and 1.
Yeah, that is what. Yeah, you're correct. So this is the once you start with the finding eigenvector, you end up with this equation.
X1 is equal to X2 minus X3.
Yeah. Here X1 is equal to X2 minus X3. So here it tells you we have 2 free variables, X2 and X3. So one by one you will start choosing. You can choose first. X1 is X2 is 1
hour late.
Yeah.
We just have 1 hour left.
Yeah.
Doubts, I hope
So
we
you
can
spent 50 minutes only on one question.
Yeah, we have discourse, I guess, to discuss all the concerns there.
Yeah, I hope. Yeah, he started with eigenvector. So I don't think it matters. So here, see, you have 2 variables, free variable. You will choose X2 is equal to 1 and X3 is equal to 0. You can choose even. Okay, and now X1 is going to be your 1 and then 1 0. So sorry, yeah, eigenvector is going to be this one. Okay, and if you choose again X2 is equal to 0 and X3 is equal to 1, then you end up with the 1 0 1. This is the next eigenvector. Sorry, eigenvector you'll get. So
anyway, we can do that. Let us not waste move it.
Yes.
But the answer for this one is not coming. So that's what I was saying. The ultimately the projection value, the answer given here is not coming. So we wanted to check where is the mistake we are doing. Why none of the 4 options the answers are coming.
Okay.
This is a PYQ question, so that's why I'm raising this concern. If any of them you in the group, if they have done it, they can share.
Yeah, actually, I will try to paste the solution of that.
Yeah, this one. Yeah, this is required. Okay, whether we should take this, X bar and U2 and X bar U3, we should take it or not?
Yeah, okay. Just a second.
The X bar transpose you have to take. There is no doubt about that. But answer we are not getting.
No, my question is that suppose the 1 dimension is given. What is the meaning of 1 dimension exactly?
You have to always take the X bar. You have to always center it. If you are taking Xi, if I take Xi with Ui, you have to also add that with X bar.
It means M plus 1 plus M plus 1 to D. M plus 1 to D.
With the other X bar times the other vector, you have to do the dot product. That is there. That is already the TA also in other days also he has clarified it. But if you do that, you are not getting the answer. That is my concern. If any of you have done this question, have you got the answer? So that is my query.
Okay. Just a second. The solution
So
will be pasted.
let us move out of this question. If you can post this, the solution for this, it will be great. Because answers we are not getting.
Sir, we can discuss this solution at the end of the class.
Yes.
Yes, sir. Please.
But revision, if I will do someday, it will not take time because we have already did, and week 5, nothing is there. So we only week 6 contain bit. Okay, so we'll quickly do that. Okay, solution will be given in the I just said to TA, he will post the.
Okay, sir. Post the solution, we will do it.
Because in the discourse, it was mentioned the practice assignment question number 5, the answer was wrong. So similar to that, I want to check the answer is wrong or not. The answer mentioned in the practice assignment on week 7, it is mentioned it is wrong. The TA has clarified in the discourse. So here
Okay,
also,
okay.
here also
Then
you want to clarification. You want to get a clarification whether the answer is wrong. Then we'll get a confidence.
if TA is saying, then it is. Then
That's
there is
a
a
different question. That's a different question. That's a week 7 practice assignment. So this one, if you can clarify the answer is wrong, then we can get.
It will solution will be pasted in
Yes.
chat. Sorry, in the Discord.
That is
fine. Fine. That will be fine.
Okay. So in this revision session, we are going to cover only 2 weeks, week 5 and 6. And week 5 is, very less contents are there. We just need to know the what are the matrices we have. The complex matrices we'll see. Hermitian matrix is kind of I'll let you know Hermitian diagonalization of Hermitian. Diagonalization of Hermitian. Because many times you are finding the eigenvectors, eigenvalues. So just now I have also find. So nothing is there. I will just tell you some properties. So complex matrices are going to be those matrices where the entries are going to be the complex number. Okay, only that is the meaning of the complex matrix. The entries are going to be some complex number. That is a complex matrix. The Hermitian matrix. Hermitian matrix is a matrix which have this property. If you do the conjugate and then transpose, it will be the same as the matrix. If have matrix with such property, that is called Hermitian matrix. And unitary matrix is that matrix which have, we do the in short form we used to write here as a star. Okay, sometimes we used to write AH also, Hermitian of it. And the unity matrix is such matrix which have this property: A star A is equal to identity. If you do the Hermitian here, okay, if the Hermitian means both these operations, transpose and conjugate. If you follow these two operations on the matrix, means conjugate and transpose, that is our A star. So if you have this, if the matrix have this property, we'll call it a unitary matrix. Okay. If you relate with real matrices, so this is going to be if your entries are real, then this Hermitian becomes symmetric matrix. Okay. This Hermitian becomes symmetric matrix, and this unitary become orthogonal matrix. You have already seen these all. So there is a broader meaning of the unitary and Hermitian when we are playing on the complex number, and some different name is given for the symmetrical and orthogonal. The name is Hermitian, where we are doing the conjugate. This because of this conjugation and then transpose is the main changing the key point here with the difference between the real and complex. I hope you know it already because we have done this too. Week 1 to
orthogonal in the real space and the unitary in the complex space.
Yeah, this is for real space or real. You are putting in the matrix real numbers.
Okay,
so,
real
and here
numbers,
it is a complex.
Orthogonal in real space? What does it mean?
Orthogonal means the entries are going to be real number if have same property. Means here orthogonal means what? A transpose A is going to be identity. And symmetric means A transpose is equal to identity. We are not adding extra thing conjugate. Why we are not adding? Because entries are real, so it will not affect the conjugate thing. Okay. So if it is a complex, then the name is different, Hermitian and unitary. But having the same property, you can see A transpose here. The conjugate word is added here more. Otherwise, see the same things are there.
Conjugate means you just change the sign, no, sir?
Sign with whatever with the I we have, that
with
will
the
change
complex. Yes. Okay.
Only complex sign changes.
In unitary, it is not transpose, no?
In unitary also here A star I wrote, no? So here means here A conjugate.
A transpose conjugate.
Okay. Here that is what here A Hermes sometime used to write like this.
For complex it is unitary, for real it is orthogonal.
This is what the meaning. All three are same. Either we used to say A star or AH or this one. Transpose and conjugate.
In what property unitary and orthogonal are different?
Yeah, so some properties I have some property we have. So here the first property here, it have the real eigenvalues.
Yeah,
you
correct.
can check, even always it have the real eigenvalues.
Yeah, always real.
And another property is the eigenvectors are going to be orthogonal. Not only orthogonal, means orthogonal is here. So here the eigenvectors are going to be orthogonal. Eigenvalues are going to be real, and eigenvectors are going to be orthogonal. This is the property of Hermitian matrix.
So this is the difference, because in the
why
real,
this real? Why this real? See, the surprising thing is that the entries are here the complex, but the real values are eigenvalues are real. This is a surprising thing for the Hermitian matrix.
Yeah, and this is the difference, no, from the real symmetric and this Hermitian.
Yes.
Right, no?
Yes.
And this is the only difference, or other difference properties are also there from the real symmetric?
No. This is the in the symmetric have already the real eigenvalues, because the entries are already real.
Correct. It means this is the only difference, right?
Yes.
Okay, fine.
And the Hermitian don't have any specific property. The eigenvalues we cannot say. The specific property is, if we have eigenvalues, if we find the eigenvalues, okay, let's say lambda, some eigenvalues we are getting, okay, if you find the modulus of it, it will be always 1. This is the property of unitary.
That means it is orthonormal also, does it?
Yes.
No, eigenvectors may not be orthonormal.
Magnitude 1 means the orthonormal, because they are orthogonal as well as.
No, this one meaning is, I am saying for the eigenvalue here, this lambda is
eigenvalue also. Okay.
So this is
Sir, could you please repeat again for
so
unitary?
here the property of unitary is that if let's say eigen, okay, if you find the eigenvalue lambda, okay, lambda 1, lambda 2, whatever the all, okay, for any, how many eigenvectors you are finding, if you find the absolute value, because here the absolute value, why I am saying here, it may have the complex eigenvalues, okay, these eigenvalues may be complex also, okay, maybe 1 plus I or 1 minus
In
I, these are the
Hermitian, they're all
eigenvalues may have.
real.
But if you find
Hermitian, they are real.
Sorry?
In Hermitian, eigenvalues
in
are
Hermitian it is
real.
always real, but in the unitary it may complex. But if you find the absolute value of it, okay, if you find the absolute value, which is nothing but, if you find the absolute value here of it, this is going to be 1 plus 1. Okay, 1 plus 1 square, which is root. So this is not going to be
this is the norm, no? Norm.
No, this is not norm. This is called absolute value of complex number. Some different name is also.
There is no name of the norm in this complex.
This is not the concept of complex number. There is don't have this.
I suppose
this is absolute value.
Okay.
So in unitary it has to be 1, sir.
But in unitary, see here it is coming 2, no? But here in unitary matrix, the whatever the eigenvalue you will get, it is going to be 1 always.
But only difference is that it can be also complex number, isn't it?
It is the
complex. The eigenvalue can be also complex.
Yeah, and eigenvectors may not be orthogonal.
In a complex vector, suppose 1 plus v and 1 minus v. Two elements are there. Then how we will calculate the norm or this absolute value in the vector form?
Sorry.
1 plus I and 1 minus I. 1 plus I and 1 minus I. Right.
Okay.
Then how we will calculate the norm or this absolute value of this vector?
So this is just a formula. If you have this complex number, absolute value is going to be
under a square plus b square. Okay. For this, but if in the vector form, if it is written in the matrix vector form, a plus ib and a minus ib, 2 types.
Where it is no a plus ib, a minus ib.
No. In the column form.
Okay.
There are 2 elements.
Vector you are saying. You have suppose a vector in.
A vector. Yeah.
Okay.
This is a vector. Will have some norm.
So in this case, it have no norm. The norm is going to be inner product with the v. So this is going to be nothing but B transpose V, which is going to be A plus IB, okay, A minus
Okay.
IB. You have to follow that. Not only this one, you have to do the conjugate of where. So here,
Yeah, yeah,
here we have to
yeah,
do the
yeah.
conjugate
We,
also. So this is
conjugate
going
we
to
have
be
to
A
take.
minus
Yeah.
IB.
A minus
And
IB.
this plus. And now
Okay,
the
we
this
have
is
to
going
take.
to be,
We have to take V transpose V. V star V.
yeah, V star V. That is called, yeah.
V star. We have to write V star V. Then we will get the, what we will call it?
Where,
No, we will call it norm or
yeah, norm, it is just norm.
it is a norm, no, for this vector.
Yeah, it is norm. Here it is called absolute value, but here it is norm. So
Okay.
this is okay. So many people getting confusion. So this is a vector. Okay, this is a vector in
That's why
complex.
confusing. In the case of vector, which is having the complex elements, we have to calculate the norm like this.
Norm
But
like this only.
yeah, but like V star V.
Yeah, V star V.
And in case of the complex number, we have to calculate the absolute value of that complex number, right?
Yes.
Okay, thank you, thank you.
All of you are getting it? Is
Yes,
it
sir.
clear? All
Yes,
of you?
sir.
Okay. So this is the complex thing. These are some property of Hermitian. And if you want to say,
Sir,
I just
Yeah, I have this.
yeah. What is your doubt?
Yeah, in unitary matrix, like
Hmm.
we are always getting this lambda means eigenvalue is -1 or 1, isn't it, sir? So
No. Eigenvalues, no. Absolute value of the eigenvalue. Means
yeah,
here
yeah.
you have
So
not -1 also. It is going to be always 1.
always 1. Then why should we put this what to tell this mode function?
See, if you calculate the eigenvalue of this one, 1 upon root 2 plus I 1 upon V2. What is the eigenvalue of, sorry, absolute value of this one? This is going to be 1 by 2 plus 1 by
Yeah,
2, which is 1. Correct? Is it? As the
yes,
formula
sir.
is this one.
Sir, doesn't I make it as -1 by, I mean, but my
So just a second. So this is 1, right? So this is one eigenvalue. Sorry, this is one complex number. Similarly, you may have other one also. See, for complex number which have absolute A plus IB. Okay, if suppose if you calculated absolute value which is 1, so you have infinitely many such a complex number. Okay? Not only one, you have infinitely many complex number which have which have the absolute value as 1. Okay, so you don't think it is always going to be you see, one example I have given this one. Okay, another example is if you just calculate 0 plus I, this is one complex number, right? If you just suppose you want to calculate here the absolute value of it, this is going to be 0 square plus 1
1.
square, which is going to be 1. So this is another complex number which have the 1 as absolute value. You have infinitely many minus 0 minus I, or just you can write minus I. You have so another so many complex number which have the absolute value as the 1. So, but the unitary matrix have such property, or unitary matrix have this property where the eigenvalue is going to be the absolute value of the absolute value of the eigenvalues is going to be 1. So don't be worry that okay 1 is coming, so only the fixed number or no. There are infinitely many I complex number which have absolute value 1. Okay,
Yeah, sir.
is it
Okay,
clear?
sir. Yes, sir. So and this oh, 1
Is it
plus
clear?
I you have given mode, that will be value, isn't it, sir?
Sorry, I'm not.
Yeah, 1 plus I whole mode is like a
Sorry,
value of unitary matrix can have.
sorry, sorry. Now I will hear you. Could you repeat it, please?
Yeah, I am telling that this you have given one. Yeah, this 1 plus I mod whole mode in above, little bit above. So this could be a value of a unitary matrix, isn't it, sir?
1 plus IV, this
Sometimes.
one.
Yeah.
No,
This could be a this.
No. So this one is never going to be a one eigenvalue, because here the absolute value is √2. So this number is never going to be the eigenvalue of any matrix, any unitary matrix, because it have absolute value as a √2. Okay. Clear?
Yes, sir.
Okay. So some other property Hermitian have. Okay. Not only Hermitian, here the combining property I'm writing. Okay. For unitary also. Both are actually diagonalizable. Okay, you can check it. Both are diagonalizable. That is why the next, if you say it here, these are the Hermitian matrix diagonalization. Hermitian matrix is always diagonalizable. Okay, not only Hermitian, unitary also.
Sir.
Yes.
This no, sir. This is maybe wrong sometimes. Like every Hermitian matrix is diagonalizable, but is it also for unitary too?
Unitary means you are saying Hermitian. Sorry, means matrix is going to be a unitary.
Like Hermitian matrix.
Is unitary also diagonalizable?
Yes, unitary also always diagonalizable. So why we are specifically studying here is, see, I added from my side. Okay, I added my side. You can check it in unitary also diagonalizable, but this is a spectral theorem. Okay, this is
On the
guaranteed by
contrary,
spectral.
I think what question he's trying to ask is, if a matrix is diagonalizable, can we confidently tell that it has to be either unitary or Hermitian?
No. So
that's what it said. Reverse is not true.
Reverse is not true.
Reverse is
if
not
it is Hermitian, then it is diagonalizable.
Yeah,
but if
it
it
is
is diagonalizable, it does not mean
it's not sure that it's
it
Hermitian.
may not be Hermitian. Just like that, orthogonality also there. If the Hermitian, then and it is having the eigenvector corresponding to distinct values, then it will be orthogonal. But if it is orthogonal, then it cannot be Hermitian. Am I right, no, sir?
Yes.
Sir, could you please repeat once again?
Mean to say, if Hermitian, the matrix is Hermitian, then it is always diagonalizable. But if your matrix is diagonalizable, it may not be Hermitian. Means, sorry, yeah, it may not. You have different matrices, which is not necessarily the Hermitian, but yeah, diagonalizable.
Hermitian is itself a magician. So everybody cannot be a magician like that.
Yeah, correct. So this don't be confused with this one. You can because she asked her out because this word is a bit confusing also.
Yeah,
because this is a wider gap. Okay, this is not even a small gap. This is a very wider gap. Diagonalizability is for any matrix can diagonalizable, but Hermitian is a very specific matrix. Okay, this Hermitian is a very special matrix, and it is guaranteed by a spectral theorem. Okay, that says Hermitian is always diagonalizable. That's what.
Okay, sir.
And you can add from my side also. Unitary is always also diagonalizable always. Okay, this is not guaranteed by spectral also. But spectral, you can check it always. The unitary is also diagonalizable always. So these are the property, and diagonalizability. I will leave the thing is that, because what is the way, see, each time. So I'm skipping these lectures. The reason is, many times you are doing just eigenvalue, eigenvector. So just now we have found also. So the process is, if you have matrix is given, okay, a matrix is given, you have to do a minus lambda I. We tried it also. Okay, and you have to find the determinant of it, and you get to 0, and you'll find the some eigenvalues. You'll get eigenvalues. Now we will substitute there, okay, one by one each time, and you will write a system of linear equation. You will start whatever the values you will get here for x, that is going to be your eigenvectors. Okay. Once you find the eigenvector, you will use to find p. Because why I'm very fast, many times we did already in the real case, we have did the diagonalizability. The same way it is going to be.
P means a unitary matrix, no?
Yeah, P is not unitary matrix, means means here we have to, once we find the eigenvectors of this, eigenvectors we found.
Yeah.
Then first just do the normalization. Normalization means just divide by the norm. Okay, it will be normalized. Now suppose you got 3, so you have suppose you have a 3 cross 3 matrix, okay, and you have 3 eigenvalues. You got lambda 1, lambda 2, and lambda 3. Okay. Once you got, then let's say v1, v2, okay, and v3 eigenvectors you got. Okay. Just divide by the norm. It will be normalized. This is case for, I'm saying for this, Hermitian case. Your matrix is Hermitian. Okay. Your matrix is Hermitian. So we got this eigenvectors. Now what you will do, you can write A as a P inverse AP, okay, where P is a matrix, okay, where P is going to be your, okay, V1 norm of V1. The columns are going to be of P is this one, V2 norm of V2. Okay. Now columns are going to be P of P is this one, P3 norm of, means the vectors, whatever the vector, normalized vector you will get. That is going to be your P. So here is this is T here, I just put from you. And D is going to be your eigenvalues.
Diagonal matrix.
This is what it is. This is the spectral theorem. This is the guarantee thing by spectral.
P inverse.
Yeah, it's depend on sometimes many how in the lecture you
Sometimes
can
it is written P inverse BP. Somewhat it is like A is equal to Q delta QT.
It's many times you can say P inverse. All are actually fine. Or many times T is
because
equal to
P inverse is equal to P transpose.
Yeah, here is here we are taking the Hermitian is this one.
P star we can say
A star Hermitian. So in this case, this P is going to be unitary matrix. This is unitary matrix. So in place of writing inverse, I can write here A star. Sorry, P star.
P star D P.
Because this here we discussed just now, unitary. Where is that unitary?
Sir, it will be P star D P or P D P star.
See, unitary matrix is A star A is equal to identity. So unitary matrix is U star U is equal to identity, means here it says U inverse is nothing but U star.
U star, correct.
So in place of E inverse, I can write P star, right? Inverse, I can write P star.
No, I am telling you in the formula, in the Hermitian matrix, A is diagonalized as Q delta Q transpose or Q star.
Q, okay, delta is
Q delta Q delta. Any delta, no problem. D, you can write D also.
Delta, see, so many you have delta.
No, capital D you can write, D.
Okay.
No problem. D and Q star. This formula. This formula is equal. That is the same.
Same. Yeah, that is what I was saying. Here is
Q1 D, Q1 delta Q2.
No, that is SVD. That is SVD, no? That is different. This one is different, no? In the Hermitian diagonalization, no?
See, many places could be written like this, or maybe it's depend on lecture. Okay, so let me check the
No,
lecture. How in the lecture it is.
Yeah, yeah.
Let
Go into the lecture, sir. Go into the lecture because we are following that one. It is confusing.
I have seen mostly Q is there when it is orthogonal.
Yeah. They are using unitary in the case of Hermitian. They are using Q in the case of real in the lecture.
what?
It is mentioned that a matrix A is unitarily diagonalizable if there exists a unitary matrix U such that A is equal to U delta U star, where delta is a diagonalizable diagonal matrix. Yeah, this is the observation. Definition is that.
This is the same. A is Q, D, Q star is the same thing.
Yeah,
Okay,
this one is
QD
same
good.
thing.
Okay, so
But
yeah,
what
so
but what you wrote, sir, no? A is equal to P star DP. Is it the same or different?
yeah, it is correct. Okay, this is also correct. Okay, this is also correct. But
How
let's stick with this.
how that one is correct? That's what I want to
Yeah,
know.
correct. The reason is P star is nothing but P.
No,
Because
no,
of this,
that I know. But here in the sequence changes, no? The left singular value and right singular value different.
no
How
matter.
can we
Okay, let me say, let me write like this. Okay, so if you are
when we write a D is equal to becomes P.
okay, let me.
A,
I will be
yeah,
on whatever you are saying. Let me be on
yeah,
that.
yeah. Please check it, sir.
I'm
Because
just. I'm just small changes I'm doing. I'm not.
yeah,
I'm not changing anything. Now I'm saying this is Q, and now this is Q star. Okay. Now it is fine. Is this fine? So
not final. So you took transpose. Why you are taking this conjugate transpose? We have to take conjugate transpose of the A also, no? If the equality sign is there. What I mean, what is the standard formula? Go to the.
so this is the standard formula. This is the standard formula.
Okay, and the above one is the same or the different? That's why I know.
This is the same, but you can leave it. You can leave it. Okay. You for the time being, you can leave it. Okay.
Okay, forget it, sir. Okay, so
Yeah,
follow
forget
this one
about it.
only. Follow this one
Yeah.
only. Okay.
Forget about
Because
it. This is
we are
okay.
confusing with that. Maybe it
Yeah.
is
Okay.
correct,
If
but
you're
we are.
confusing,
Yeah. Please.
this is the standard one. If this is added from my side, okay. I
Yeah, no problem.
convince you both are correct, but if you want to stick with this one, that's totally fine. Let's be on this.
Okay, fine.
Okay. QD Q star.
That is okay, fine. That we are habituated with that one.
So, sir, similar to this spectral theorem, you have got another Scores decomposition, isn't it?
Scores?
SCHUR scores decomposition.
Source
decomposition.
So is this in that?
Is this the same as SBT or it is different?
No, yes. So source decomposition is different. That you are decomposing. So that is source, not because source theorem is there. Source theorem, many will different pronunciation. Okay. So here you have a matrix. You used to change. Again the P inverse kind of using that. You are changing with upper triangular matrix.
Yeah. Source theorem is T, sir. In place of D, it is T. Upper triangle.
It is going to be T.
Yeah,
upper
because
triangle.
confusion is there. Yeah, it is T.
So this is upper triangular matrix.
A star, sir. P star. Yeah, now it is okay. In place of D, it is T1. That's all.
So if
you are
given a matrix, sir, say a 3x3 matrix, how will you arrive at this upper triangle?
So this is a long process. Okay, you can follow the. This is a long process. No, you have to
very
clockwise.
long.
You have to do the. You have to do clockwise. Means Once you done with this part 0, then you have the inner part, and again you have to follow the same procedure to get to in changing the upper triangular form. You can see how the process is in the lecture. It is you have to
It is
do
in
the
the
A
week 6.
transpose
It
and
is in week 6, na? It is.
is it in week 6?
Yeah, I think it is in week 6.
Yeah, no. It is, I think, week 5.
Week 5, actually.
Yeah,
Week 5.
Actually, source decomposition
Here
is
it
that.
is. Yeah.
This is the source decomposition. Any square matrix, it will operate on any square matrix n by
Any
n,
square
right?
matrix. Yeah.
And 3 or 4 steps are there. May I say that step 2 or 3?
Yeah, there are steps are there.
Compute eigenvalues and eigenvectors, okay, of that matrix, lambda 1, lambda 2, lambda 3, like that. And so by solving the equations, okay, and normalize the eigenvectors and use them as columns to construct the unitary matrix U or P, like that. After calculating this, you have to compute that upper triangular matrix as U star AU. We have to calculate AU first, and then we will calculate with the U star. The matrix T will be upper triangular. This is the standard procedure, but it is a long process.
Yeah, it is a long process.
It will come in the examination also.
It may come.
Yeah, very difficult. Very difficult.
It is a long process. I know it. It is a long process.
But there are 2-3 questions on this I have seen in PQP.
Okay.
Very long question.
Very long question.
This theorem is part 1.
And a Hermitian matrix is unitarily diagonalizable. This is also the property of the Hermitian, right?
Yes, Hermitian matrix is triangle. So the steps are here mentioned that.
Yeah.
So first we have to find the eigenvalue and eigenvector. Okay, let me just a second. So okay, so the procedure is, once you find the eigenvalue and eigenvector of, okay, see, okay, so the thing is that, okay, suppose you have a matrix A, okay, and you find the eigenvalues and eigenvectors, okay, vectors you found, okay. So suppose this matrix is not diagonalizable, okay. Suppose this matrix is not diagonalizable. What is going to be in this case? Suppose you have matrix A, okay, where you have the eigenvalues 1, 1, and 0. Okay. Suppose you have this eigenvalue 1, 1, 0. Okay. And for one eigenvalue, which is a repetitive here, you are getting only one eigenvector. Let's say V1. Okay. And for this, you will get always V2. So you have 3 eigenvalues. Okay, which is a repetitive 1, 1, but you are getting only 2. So in this case, your matrix is not diagonalizable. Okay. This is the case for not diagonalizable, because only you are getting 2. For 1, you are getting only for this one only you are getting 1 here, V1 vector, eigenvector. If it is diagonalizable, then surely you will get another vector, let's say V3, or maybe another vector for 1 itself. You will get 2 eigenvector. But here the case is only 1 eigenvector you are getting. Okay. So it is not diagonalizable, but we can do the triangulation. So what is the next step? You will choose a vector, okay, U, okay, or V3. Okay, you will choose a V3 which is orthogonal to what is independent to these 3. What is written here? Orthogonal. Okay, if you have Z1 basis and make it the ortho normal. So you will do the, okay, you will choose the orthonormal vectors. So you will choose V3 as an orthonormal vector, which is orthonormal to these two. Okay, if these two are not orthonormal, okay, if suppose these two are not orthogonal, use the Gram-Smith process to make it orthonormal. Okay, use Gram-Smith process to make them orthonormal. V1, V2, orthonormal become orthonormal. Choose V3, which is orthonormal to V1 and V2. Once you choose, okay, just make a matrix U. Okay, then the form, if you do the U, okay, if you write like this, A is equal to, or maybe you can write you can write A as a, or find the matrix of this one, form a matrix using V1, V2 and V3. Okay, let's call it U. Okay, once you find U, then just U star AU. If you do U star AU, this is a big process. Okay, if you do
Sir, here one question I have. In the lecture, Z1 has been taken as a eigenvector, right? Corresponding to lambda 1, right?
Yes.
But when they calculated other values, orthonormal, two other orthonormal values, AU and AV. When we calculate it, by the Gram-Smith theorem, they take this first one as the basis. Okay, and then take the projection of second one, orthonormal projection of the V1, Z1, and the orthonormal projection of B2, B on the Z1.
No, there is not orthonormal projection. Why will do the orthonormal projection?
Orthonormal basis, we have to form the orthonormal basis. Let ZUV be the orthonormal basis. Means UV you have to calculate, na?
You have to find the U and V.
Yeah.
New vectors.
Yeah, new vectors. That should be orthogonal to Z1.
Yeah. Yes.
And that will be done by the Gram-Smith, right? Am I right?
Gram-Smith process. Yes.
Okay.
That is what I am doing here. No, once you found that is what
there is no need to take independent vectors. One of that can be taken as the vector, first one. Is it so?
Yes.
Correct. Okay, fine.
Okay. So by this way you will form U, and if you do this one, U star U. Okay, if you do this one, then you'll get a kind of this matrix. If you do U star U, sorry, U star AU, if you do here as here, so you'll get you may get either it could be itself upper triangular. If you are not getting upper triangular, then this part, this column is become 0, and maybe this part is non-zero. Then just block this matrix, and let's say this matrix is B. And again, now this just find the again for this B matrix, whatever the above process you did, again do means find the eigenvectors.
Repeat the same process.
Find the eigenvectors, and again try to triangulize. Means now you are triangulizing this B upper triangular. You are triangulizing now B this matrix. You are doing this one. Now this will be the same process we will do. Then now this will be in upper triangular. So slowly it will be triangulized. It will be. It should be done by example. Then it will be more clear. I think there is a tutorial on this.
Yeah, it is a tutorial on that.
Yeah, so that's totally good then.
But what happened, sir? In the lecture itself, go to there. The question is, I think what has been done after final answer go. It is wrong. I confirm from the TA also. That's why we are very confused. The last line was wrong. It was.
That last, I think. Okay.
Yeah, it is wrong. Already I have mentioned it.
Okay.
TA also confirmed it.
The final answer is wrong.
Final answer is wrong. In the lecture itself. No, not in this. In the proof. In the proof itself.
In the proof.
The example is given, because that was the main thing we do with that. When I was doing the example one by one, it was very difficult to reach at that point. Because I was believing that it may not be correct, may not be wrong.
Okay.
Because professor, how can professor do wrong? But I confirmed with the TA. He is also telling that it is wrong.
Yeah,
You can also
yeah.
see
So
this.
this is okay.
Not here in the lecture.
Yeah, I got it. I got it. It is in the lecture.
Yeah, it is in the
But
lecture.
I thought maybe there should be an example in upper triangulation. Okay, so,
Yeah, one we can do.
okay. But this is a process. Okay, this is the process you can follow too. It should be one example on that. Okay, already in the lecture, but that is wrong.
So that V1, V2, can you clarify, sir, what you told? This
V1,
V1.
V2.
Yes.
Suppose you have a repetitive eigenvalue and you are getting only V1 is one eigenvector and V2 is for 0. Okay.
Yes.
But here it is a repetitive, but in this case you are getting only one eigenvector, not two eigenvector.
Yes.
If it is two eigenvector, then it is diagonalizable. But if
Okay.
it is not, then it is not diagonalizable. Your matrix is not diagonalizable.
So what is
In
the
that
next step?
case, then in that case, what you will do, you have to find a third vector V3, which is orthogonal to this V1 and V2. Okay, and using the third eigenvector, you will form your U, which is like this.
But V1 and V2 also have to be perpendicular.
Yeah, if they are orthogonal, then fine. If not, okay, if not, then do the Gram-Schmidt process to make them orthonormal.
Even for V1 and V2, and then with V3.
Then add V3.
Oh.
Okay, if not, then do the Gram-Schmidt, make them orthonormal. Okay, make them orthonormal, and then choose the V3 third one. Okay, which is orthonormal to V1, V2, V3. Means V1 and V2.
Okay.
And now, if they are become orthonormal to each other once, then form U. Write as a column wise for that matter.
Okay,
Now,
sir.
if you do the U star AU, you'll get a matrix that may be directly upper triangular, okay, and may not also. If not directly upper triangular, then this column, okay, here is some non-zero, and this below of it is 0, okay. That part may be till maybe this part will be remain, okay. This part may be here, this part is remain. Then do the same process, whatever you just did above, make a block of it, means make the matrix, choose that matrix from there, and do the same process and make this matrix in the upper triangular form. And once it become the upper triangular form, then see the final answer is, means here, let's say by doing this, suppose this matrix you are doing this, and for this B matrix you got U2. Suppose here is this one is U1 you got, let's say you got for B is U2. U2 you got, okay. So final your matrix, once you are doing this triangulation, this will be U2 star, U1 star, A, U1 and U2. You do this process. So this is, you see, this one should be done by an example. If I am telling, you will not get. If you are already seen the lecture, then totally fine, you will get. Otherwise, it will be a tough thing. It is a longer process.
And what is the property of this upper triangular matrix? Where we will use it? What benefit we get from the long process?
The use is simple, as the diagonalization is make the matrix as a simple form, right? It's look like very simple, many places zeros. Okay. If it is, so see why we are doing this diagonalization. Diagonalization is make our matrix easier. At many places you will get 0. Okay. But if not, your matrix is not diagonalizable. Suppose your matrix is not diagonalizable, we have to, if you are doing a very big data, okay, so we have to find again some simpler case, no? Then we will do the triangulation, because at least if you are not able to put many zeros at many places, let's do the below part 0, and let's say the above part is not 0. So means in compare of the original one, this is a bit easy. This look like a bit easier, no? This dealing with this matrix is a bit easier in compare of original one. That is the reason.
It is less difficult than the previous one. It will be more easier than the previous one, and the
yeah.
Okay.
why we are doing this all to change the matrix in the simpler case.
This is called decomposition.
Yeah, this is a decomposition. We are decomposing our matrix in some simple matrices.
Yeah, reproducing the matrix in the another form, right?
In another form.
Okay.
So that whenever we use some property, not only some property, rearranging data. See, this form doesn't change the property. This form is not changing any property. Our matrix become now simpler, but not changing any property. So it will apply if very big data if you have, okay, so many properties, some you are farming the, if you have machine learning, okay, you are whatever the feature given, okay, you will change in the matrix form and use the decomposition to change it to simpler form. Now dealing other things will be easier on this once we change in that, because the property is now not going to change anyhow. This property is for this matrix is not going to be changed anyhow, but all other things can be done easily, because the reason is you have to do so many addition, multiplication, then computer can do easily, right? Because at many places we will get zero and easily done very fast manner. That is the reason we are changing, or that is the main reason decomposing.
Correct.
So let's move on to the week 6. And week 6 we have mainly SVD. Yes.
Sir, one down. Every Hermitian matrix is a unitary matrix.
No. Every Hermitian matrix is not a unitary matrix. The simple contradiction is Hermitian have the real eigenvalue, but unitary don't have. May not be.
Okay, sir. So we can say that every unitary matrix is a Hermitian matrix.
Every unitary matrix is Hermitian. No. Unitary
Different.
may not be Hermitian. May not be Hermitian.
Any matrix can be Hermitian only if the A star is equal to A. If it is not, then it is
the
not.
simple thing is no relation between these two. Okay, don't be related.
There is no relation at all. One relation is unitary. The Hermitian matrix is unitarily diagonal. This is the only. Am I right?
Yes.
This is the only relation in unitary.
Otherwise, don't relate it. These two are different matrices.
Okay, sir.
If a matrix is Hermitian, then it can be written in the form of diagonal matrix and the unitary matrix, and the left singular value and right singular value, like that. Am I right?
Yes.
Correct. Okay. Very confusing.
Yeah, here you are not studying in a very detailed manner. So that is why it is a bit confusing.
The name linear algebra is very unjustified. It should be a curved algebra.
No, but if you in the whole matrix case, this linear algebra is very subject. Okay, so in whole matrix, in mathematics only, the linear algebra is very easy one topic or very easy subject. Other mathematics topics are even more tougher than this one. So this linear algebra, this is not tough. Okay, you study here, you are whatever you are studying. This is a partial information. How much like whatever you want to study, or whatever the things you want to use in machine learning, those part you are studying here. That's why it's like a bit difficult. Otherwise, this linear algebra is not difficult. Totally not difficult. Very easy.
Absolutely right, sir. You are telling.
Only
because
the
we are learning partial thing. We are learning the partial thing without going to the basic thing. That's why we are facing difficulty.
It's that's why it's become tough.
Correct. Okay, let us proceed, sir. Okay.
So this week 6 is SVD, and SVD is again, so simple reason why we are studying the SVD. The reason is till week 5 we are dealing with only the square matrix, and try to change in a simpler form, means diagonal or triangulation, or maybe or triangular form. Okay, Okay, this form, your matrix is a square matrix. But suppose the case is when your matrix is not square, it is a rectangular. But we have to think about again, we have to think the simpler case of this. So to think the simpler case, there is a form SVD, singular value decomposition, for the rectangular matrices. And this, how will change this? This form is nothing but this. If you have this matrix A, then this matrix could be written as Q1 sigma Q2 transpose, where Q1 is a square matrix of order. Let me write the order here first. M cross n for sigma. So sigma is going to be the order of M cross n. Whatever the matrix have order, the sigma have the same order. Okay, and beside these two going to be the square matrix. And how this could be square matrix means what is going to be order here. So order you can easily make it. This one for M cross n, and this for, so this for Q2, this will be n cross n. Okay, so Q2 is going to be of order n cross n. Okay, and Q1 is going to be order m cross n. That's all. Okay. So this form is called singular value decomposition. This form is called. Okay. Now the question is, now what is going to be the steps to form this? So steps are simple. Okay. We'll use the eigenvalue eigenvector property. But this matrix is not square, so we cannot do. So we can do by doing A transpose A. If you do A transpose A, okay, then it will be now the square matrix. Okay, this will be a square matrix. Now you can find the eigenvalue
and symmetric also, no? Symmetric also.
Yeah, symmetric also. This could be square matrix and symmetric also. Now you can find the eigenvalue and then eigenvector. And these eigenvectors, yeah.
So we can calculate A transpose also.
So yeah, we'll do that. So let me even you can confirm.
Yeah.
You can confirm.
Please.
So this eigenvectors are going to be for which one? This one or this one? A transpose A.
For Q2.
For Q2.
For Q2. Okay. So be sure with this. If you are doing A transpose A, this will be this will be this. So eigenvector, we'll use this eigenvector to form Q2. This eigenvector could be written as a column. Okay. Let's say you have this V1, V2, V3, whatever the thing is that you will write just a column. This will be your Q2.
After normalization.
After normalization, always be there. Okay. So whenever you are doing the eigenvector, by default you have to do the normalization. Keep it always.
Then what is Q1?
So Q1 is going to be, now if you do the, now what is that? Do the A transpose. Okay. Again, this will be a square matrix. Find the eigenvalues and corresponding eigenvectors. Okay. These eigenvectors, okay, you will write as a column wise. This will be
go to Q1. Go to Q1.
This will be go for Q1.
But my question is that in what case we should use A transpose A, and in what case you should A transpose?
If the matrix is broader, like taller, no, if it's broader, then use A transpose, because that will be smaller dimension. If the matrix is like taller, then use A transpose A.
Then suppose we are doing A transpose.
It is okay, you can do any one, but one will be easier.
You can, yeah, which one is easier? That's the best thing is, whatever the easier one, you can follow that. That's all. That is my
Okay, one thing. Second, suppose we followed another Q1. Suppose we got Q1 first. Okay, started with A transpose, and we got Q1.
No, why okay, you got Q1. Yeah, this is always the fix. Okay, this will give Q1 and this will give Q2.
Okay. Then we started. Suppose we find that A transpose is easier. started with Q1, then how we will get Q2?
A transpose A.
1 by sigma.
No,
A
again we have to
transpose
calculate. Again I have to
mu1.
calculate
No,
transpose A.
Yes, yes, yes.
Q1.
No, you don't have to. You don't have to calculate the other matrix.
That's my
You
question.
can straight away use the formula. You can straight away use the formula. You know the same vector. Same
Yeah,
vector
so
divided
see,
by
there are
the.
another steps. Once you found Q1, this will also help you to find Q2.
Yes,
The steps
automatically
are
you
there.
get it.
How that formula is one by A, I think
Yeah.
Y1 No,
Yeah, yeah, that is a
Y,
different
1
formula.
by
Sigma is
sigma.
m times u1 by sigma.
What is that formula?
Y1 is equal to
So,
1 by sigma.
The original matrix.
The original
Into the
matrix.
unit vector you have already identified it from
Yeah.
Q1 divided
Okay.
by the sigma 1 which you have calculated. That
Okay,
will be
fine. Suppose my question is here. Suppose we have started with A transpose, then whether at that time we will use A original matrix or A transpose. In some cases, I have seen that if you are started with A transpose A, then we have to use A. If you started with A transpose, then you have to A transpose in that Y1. Is it correct or not?
Yes.
This is dot product.
In this case, you have to do the dot product. So you have to do the A transpose. In this case, the upper one, you do the A, normal, original matrix A.
This is my confusion, how it is correlating. And
Do not get confused. Just try to do dot product.
Yeah, that's the best way. You do the dot product, you can solve. Correct.
The dot product of which? Original matrix?
And if you're getting it by A, then
Formal.
use A. If you're getting it by A transpose dot product, then use that.
No. Original formula is what?
For example, if A is 2, like 3 by 3, and Q2 you got in 2 by 2 form, and if by transposing it you are able to do dot product, then do that. If both are in like matching dimensions, then you don't need to transpose while doing dot product.
Now my question is different. My question is, what is the original formula for getting Y1? Y1 means, or the second unitary matrix. In the formula given in the lecture is 1 by sigma AXI. This is the Y1.
That you will use it for Q2. From Q2, if you are doing Q1, you'll be using the original matrix the A. And if you are arriving at Q2 from Q1, you do the transpose.
Why it is so? That's why this is my question.
So
why we are doing this?
It is already deduced. Na? If you go through the entire process of deduction, how they have arrived at Q2, that is already proved there. So you have to.
They have proved only for the A transpose A, not A transpose.
Obviously, if you do A transpose A transpose A will also come. You put the value as A transpose as A, you will get the answer. But obviously, it is there.
Okay, fine. Okay, if it is correct, then the formula we have to just change. If we are using from Q2 to Q1, then A, and then if it is Q1 to Q2, then A transpose. Is it okay, no? Because this point of time you cannot go inside the proof. The proof is very confusing. We have to remember what to do.
See, this one is, see, in the last it is said that, so see, okay, so here somebody says wrong, then okay, so you know this will feel this is for Q2. Okay,
this is for Q2, sir.
Yeah, this is correct. So what is the, see, if you are not following this way, okay, if you are not following this way, then the steps are first find the A transpose A, okay, and find the eigenvalues and then eigenvectors. Once you found that, and then find the singular values. Okay, singular values. The singular values are nothing but the root of the eigenvalues.
Okay, fine.
Root are the eigenvalues. And then you will use Y1. So you'll find using these values, you will find the y1, y2, and y3, where the y1 or yi is going to be what 1 upon sigma. Okay, yeah, 1 upon sigma 1.
Sigma
And
1.
then A or the original matrix, and
X1.
whatever the eigenvectors. Here, let's say v1, v2, and v3 you got. So
Yeah.
v1.
Dot product. This is a dot product or simple multiplication?
No, this is a matrix multiplication. No? This here
This
a
is
matrix. And this is a vector.
matrix multiplication. Okay.
Yeah.
This
will give y1. Similarly,
V1,
y2
V1.
is 1 upon sigma 2 and v2. And these
Yeah.
y1, y2, and y3 you'll use to find the q1. Y1.
Q1. And V1 is coming from the Q2.
V1 is coming from
Q2.
So this will be q1.
Yeah.
And
V1 is V1, V2.
this
V1,
this
V2
will
is coming
be
from
q2
Q2.
is your v1. Yeah, v1,
Correct.
v1, v2,
Correct.
v2.
Correct. And suppose we started with A transpose.
Why you are starting with A transpose?
Because I am telling why I will start. Because sometimes it's a 4x4 matrix.
Huh.
Then it is easier to get A transpose first.
So, but
then
you will not
Q1.
do this process, no, for A transpose. Why
No,
how
for
you can
square
do
matrix, both will be same size.
No,
so,
my question.
If you are doing A transpose and you are applying this formula, this will not work,
No,
right?
that's which formula we should apply for that.
No, only do the A transpose, no, as the set is that A transpose, and do those all.
I am saying that if we start A transpose and we use formula y1 is equal to 1 by sigma.
Why you are using my question is why you are using?
Because
is it said in the theorem?
Not
No,
in the
right?
theorem, but it is given in the solution of the graded assignment somewhere. It has been used. A transpose, and then formula used was A transpose V1. V1 was coming from the Q1.
And this is a solution for 6 last question, sir. So it is provided like that. A into A transpose.
Sorry.
Week 6 graded assignment solutions. Last question. So it is given as A.
Correct. He is telling here in the formula, in the solution, you see it is there.
So he did A transpose,
Yeah,
and then find the eigenvalues, eigenvector, and do these all.
Yeah.
So this formula will change, sir. Actually, if you do A transpose and you get the eigenvector, then the y1 will become 1 by sigma 1 A transpose times v1.
Okay, so here it is going to be.
I also remember the formula, but whether it is correct, whether it is not.
Correct. It is correct. It will be A transpose time v1.
Yeah.
And it will be by sigma 1, and it will be A transpose time v2 by sigma.
I checked it also. It was working fine because I used both the things. By the formula, and I again use A transpose A, both. For Q1, I used A transpose A, and for Q2, and again I used A transpose for Q1. The same result was coming.
Okay.
That is also the way, no? We can do Q1 again, Q2 again. For A transpose A transpose. I use for the 2x2 matrix so that it is easier, but it is working fine. Just I want to confirm whether it is correct or not.
It will be difficult when the two lambdas will be 0. It will be difficult.
Yeah. That's why. Yeah. You are telling now when two lambdas are zeros,
there are 3 values and 2 of them are 0.
Yeah, it becomes very difficult.
You cannot do it, then you have to do A transpose A.
Then you cannot do. You have to.
Then you have to go for A transpose A.
Yes.
Yeah, in that case we have to go A transpose A. Otherwise, it will be very difficult.
Yes.
Okay, fine. If it is working, then it is fine.
Yeah.
Okay, let us proceed, sir. We have lost a lot of time. Very calculation
but if
intensive.
all of you know it, then it is good that this is a fruitful discussion. Okay, no issues. So because almost we have done it, and now that's all the SVD. That's all the SVD means we are finding this formula. If all of you know how to find, then totally then SVD is done. Now the positive definiteness case is there, and one word is there. If the eigenvalues are positive become the positive definite, and negatives you are getting negative definite, mix up you are getting, then it will be the indefinite. That's all. And for for the function only, I will tell only the for x and y case only 2-degree polynomial. If you want to check for the function, is this positive definite or not? So this could be ax square plus bxy plus cy square. You can form using the matrix A B B C by these entries. So this is going to be 2 A B X Y. And this, if this is positive definite, this matrix is positive definite, you can tell this function is positive definite. Actually, it came from first this one to this, but you can reverse part also. Very true. So positive definite is that is not tough, totally not tough. You just do a lot more practice, not a lot more, just do some practice. As in the solvitus we have, you can easily get.
If it is in the function form, what are the formulas was the function in the function form x transpose x and like that? If the function formula was somewhere, no, I think.
Also, sir,
yes,
with respect to eigenvalues, how do you identify whether it's positive or?
Yeah, if all eigenvalues are strictly positive, then positive definite. If some of them is positive and 0, then positive semi-definite. If it is all are negative, then negative definite. If some of them is negative and 0, then negative semi-definite.
Will they give it as a diagonal matrix? That possibility is there.
Not necessary. You have to find the eigenvalues anyhow.
That is independent of the everything. Only eigenvalue dependent is the definite.
If some of them is positive and some of them is negative, then undefinite.
But in case of 2 by 2 matrix, no,
Indefinite.
easier formula is that if the A is greater than 0 and AC is greater than B square, then it is positive.
Yes. The best, I always choose the best one is just find the eigenvalues and decide that. Many times you are able to find the eigenvalues.
Yeah, it is better.
The best thing is this one. Only this is
But
enough.
if they give a diagonal matrix, means their eigenvalues are already found.
Yeah, already get that, the diagonal entries. But if it is not, then you have to find the eigenvalues. Okay, that's all the summarizing thing is there. Yeah, any doubt?
One more question, sir. When we calculate the diagonal polynomial equation for the calculating of lambda, I have seen somewhere some.
Sir, if it's a 3 by 3 matrix, then also we would use the same thing, right? If the eigenvalues are greater than 0.
Yeah, even say 3, 3, 4, 4, any kind of. This is only the masterpiece here, which will use.
In case of, yeah, it is correct. Positive semi-definite, it includes 0. Negative semi-definite, it includes 0 in the less than form, right?
Yeah.
Correct. Okay. One question, sir. In case of 3 by 3 matrix, can we write directly if the characteristic equation we just calculate for the calculation of the lambda, lambda cube minus trace of A, lambda square, plus minus of diagonal elements of A into lambda minus determinant of A is equal to 0. Is this formula correct?
This is for characteristic for the order.
Yes, sir.
This is correct. No, we can use it. No?
So what you said, lambda cube trace
lambda
A,
cube minus trace of A, lambda square, plus minor matrix, minor cofactors of diagonal elements of A.
Okay.
Summation.
This is a bigger formula. I know for only the square form, but
it is easier, sir. In case of 3 by 3, that becomes difficult. Because the only part is that the minus of diagonal element is we have to calculate separately and then write the formula first directly. And determinant of A is there. Determinant of the A you can calculate.
What is the trace of A?
Trace will be the sum of
Diagonals.
the sum of the diagonals elements.
Okay.
In case of any 3 by 3 matrix, it is not diagonal anything. In case of any 3 by 3 matrix. Because what happens when we calculate in the case of PCA, it becomes very difficult. 1 by 3 is given, just we did a mistake last in this session also. At that time, that becomes very difficult. But we can do this. I think it is working. If it is formula is okay, then it is working fine. Okay, sir.
Yeah.
Just I confirm because I got in the, I think somewhere, but in relation to this, our course, it was not there. So I just confirmed whether we can use it or not. Because we are not totally confident on the this content now, because basics are not there.
Yes.
We are just remembering the things, whatever it is there in the course. Okay, sir. Fine.
So it doesn't matter. You can check the formula. No? You can check the formula from the internet. You can say. I remember
I checked it, sir. I checked it. Then again, I am confirming here because internet is also. I think a lot of things is given in there. Everything we cannot learn in the net also. Because there are a lot of things. Everything cannot be. I think it is very difficult. That part.
Okay.
But it is working fine if it is there.
Yeah. So you can you can check from you can check this one from this formula. You can from your side. It doesn't matter.
One more confusion, sir. In case of general format of the quadratic form, we write, suppose the quadratic form is given. X square, ax square, by ax square, cz square, and 2axy, 2axz like that. So we can we write it directly the matrix A? And what is the trick for that?
That bigger form is again I didn't check even the bigger if you have this one.
No, there is a trick.
Yeah, there is a trick you can.
For the square terms, have all the square terms as diagonals. And
and
for example, if there is x, y, z, so the rows you have it as x, y, z. So what we say, the alternate rows, like if you take diagonal as the symmetry line.
Yeah.
So the alternate rows.
You have to create the Hessian matrix.
Yeah. So the alternate rows would.
If you do the Hessian matrix, then it will be. You can solve this.
Yeah. So the xy coefficient you'll have it on the alternate, like a staircase. You'll have xy, then yz, then z.
Yeah, at that time we write, the upper diagonal part we write. Then in the lower diagonal part, suppose it is 2. Suppose it is 2. So we can divide
1 1, right? 1 1 on the.
No, why 1 1? Why 1.5 or not 0.5? It is correct.
You can do that also. You can do that also. You get the same answer. If you do whatever split you do, it has to sum up to the coefficient of xy. So
this is my confusion. This is my confusion.
Yeah, you will get the same answer. I have tried it. If you instead of xy as 1 0, or you can put half, or you can put 2 minus 1, you get the same answer.
Okay, fine. This was my confusion because I was not confident whether it will give the same answer, because in the options we cannot check all the options. No? It is
the best is you create that matrix fxx at a11.
Yeah, Hessian.
At a22 and fzz at a33, and similarly you can make other factors. So you can solve it.
Okay, Alok. Okay, thank you.
So can you just give that solution for that question I raised in the beginning? That in August something, August 24, we are not getting that x1 tilde, x2 tilde, and x3 tilde.
Yeah.
Please share the solution.
If you can share the solution of that.
Yeah. I said already he will paste it.
Because it is in August 24 question. August 24 question for PCA.
Yeah. I told him already he will paste in that.
Because the answer is not matching.
Okay. Any other doubt?
For positive definite in tutorial session, they have used like determinant and a is more than 0, means the topmost minor is more than 0 as a condition. for positive definite. So we can use that also.
Sorry.
In the tutorial session, they have used determinant more than 0 and a more than 0, the first minor more than 0
Yeah,
as the
there is one
condition
thing
for
is there. Yeah,
positive definite.
there is one thing is there. Yeah, we can quickly even write. No, so yeah, in tutorial. So if it is, if A is here, this one is positive, and then minor is this one. So this should be positive, and similarly the part will go on. If it is all are positive, then it will be positive definite. Yeah, it is in tutorial that is totally correct formula.
You have to take in a step-by-step manner. If it is a 4x4 matrix or 5x5 matrix, you have to go step by step, staircase type.
Yes.
So you have to first do that 2x2, then 3x3, something like that, and then 4. And obviously the determinant is positive. And the first minor fact, this thing is positive. That is the way you have to do.
Yes. You can check that formula. That is fine. Any other doubt? Okay. So next Saturday is going to be the next revision session. Okay. All of you can try it. Okay.
Saturday you will be having a session at 4 o'clock, sir? Saturday.
It will be informed. I just need to check it. It will be informed.
Mock solution will also be provided.
In that session, Mayur going to discuss that.
Because there is a question in the mock, question number 5. That is on the rank of the rank approximation.
Even the solutions you can discuss in the net TS sessions also.
Okay. We'll discuss it.
Okay, sir. Fine.
Okay, that's going to be. Okay, thanks everyone. Thanks for joining.
Thank you, sir. Thank you. Nice session. It was nice.
Try to attend the next revision session. Okay. Happy Holi to all.
Thank you.
Happy Holi,
Thank you, sir.
everyone.
Happy Holi, sir.
Be colorful. Yes, today.
Yeah. Okay.
Thank you. Good night.